All right, let's get started. Thanks for coming to my talk. I'll be talking about my company's product in hardware accelerated similarity search. I'm George Williams, and I'm currently a director at GSI Technology. It's a hardware company, but I've worn a few hats in data science and AI and machine learning and software engineering over the years. And I've seen quite a few trends. I imagine you guys have seen a few trends as well. And one of the current trends right now that we're seeing is an increased diversity in silicon and chips in the market. So from ARM-based processors pushing into the server market, to Facebook building its own AI chips, to NVIDIA building mega data centers from their GPUs. Chips are hot again. And just to put this in perspective, just a few years ago, we were talking about convergence around these three major chip manufacturers by volume. Intel for servers, NVIDIA for gaming, and Qualcomm for mobile. That was then, and this is now. So integration has given way to disintegration. And to be sure, Qualcomm and Intel and NVIDIA, they're still strong players in the market, but we're seeing credible competition from big companies and small startup companies. Google, Amazon, Microsoft, Baidu announcing their chip efforts, and there are about 30 or 40 credible startups right now with real chip plays. And just around the corner, right, we have even more innovation to expect. Adiabatic and quantum computing systems there at the top left. Analog-based systems, Mythic set to release their analog-based neural network next year. And IBM pushing the boundaries on neuromorphic computing. And who knows what other types of systems we'll be talking about in a few years. Capsules and hyperdimensional computing systems. And so I'll be talking about my company's Silicon Innovation, where we are accelerating similarity search. So the agenda of my talk is going to be as follows. We talked about the chip explosion. I'll give you some background in my company and vector similarity search. We'll get into the product and discuss some integration case studies right now in bioinformatics and databases. And we'll talk about our early adopters program. So GSI Technology, there we are, smack dab in the middle of Silicon Valley. Actually, our corporate headquarters is in Sunnyvale. Yes. Our corporate headquarters in Sunnyvale, we're a multinational publicly traded company. We have offices in Taiwan, Texas, Atlanta, and Israel. And for about the last 20 years, we've been making high-performance memory, SRAM and DRAM. We also make radiation-hardened memory for aerospace and government, for satellites, and for space travel. And in the past couple of years, we've been working on that vector-based similarity search accelerator chip. So what is vector similarity search? So this kind of search is different than the traditional big data search, and we'll talk a little bit about that. In this kind of database, objects are represented as numbers. Typically, they take the form of bit vectors or vectors of floating point numbers. I've gone ahead and made a very small database of objects there, and they have 2D coordinates in a Cartesian space. And there are simple functions where you can use them to compute the similarity of any two objects in the database, or an object in the database and a query. And you can use that function to compute the most similar objects to a query. Often we call those nearest neighbors. We call them top K. And the K refers to the fact that typically you just want the nearest similar objects to a query, and often K number of them. And I guess it goes without saying now that the search is highly computational. And we'll go through a couple of examples in e-commerce and bioinformatics. So in e-commerce, visual search applications are quite popular. And the idea is very simple. You take a picture of something you like, something you're interested in. You upload it to an e-commerce site, possibly through their app, and you get instant visual matches from their product inventory. I'm showing an example here from Wayfair, one of our collaborators. They specialize in the high-end furniture market, but there are many apps from Amazon, eBay, Google, Microsoft, Pinterest, many others. So in visual search, the objects are images, and they can be bit vectors, often called binary codes in this space, or vectors of floating point numbers, usually called continuous embeddings. And the distance functions tend to be one of these. Euclidean, L1, Hamming, and cosine distance are quite popular. And these days, the visual search databases are pretty large. eBay, for example, has 1 billion images, reflecting their active product inventory at any one time. And so these continuous embeddings, they're often vectors of floating point numbers in a high dimensional space. And so you can use a trick like this to visualize it in 2D. This is called TSNE, T, Distributed Stochastic Neighborhood Embedding. And yes, very good. And this is part of a product catalog from a company called Flipkart, which is a big e-commerce company in India. And you can see that visually similar products cluster spatially, as you might expect. All right, let's go from e-commerce to bioinformatics. Molecule similarity is an important computational task in biopharma. The objects in this case are molecules, and they're represented by bit vectors usually, called fingerprints. A similarity function that is quite popular these days is Tanimoto similarity. We'll go through that in a second. And there are a large number of these molecule databases out there, and a few of them are getting quite large, hundreds of gigabytes in size. And the two molecules I show there, you'll notice that on the left-hand side, they're similar, but on the right-hand side, they have different substructures or functional groups, as they're typically called. So this Tanimoto similarity is pretty straightforward, right? Each molecule is a bit vector. Each bit represents the presence or absence of a functional group. That's the row there pointed in green. And the similarity distance is computed by a simple ratio of the number of functional groups that the molecules share over the number of functional groups that they don't share. And it's kind of like a Jacquard similarity, if you're familiar with that. And so this is a very important computational task, molecule similarity search, for at least the following activities. So finding seed molecules for novel drug discovery, determining the affinity of proteins in virtual drug screening, and predicting the chemical activity of molecules, often the toxicity, for molecules before expensive synthesis and before expensive clinical trials, lengthy clinical trials as well. So, I think we're going to see a lot of applications based on similarity search, and not just because of hardware acceleration, but also because of the adoption in common programming interfaces. So here you see idiomatic SQL there on the left, and the top, that's simply creating a vector database. In this case, it's native bit vectors of 4K each. And right below it, is an SQL nearest neighbor query, which is using the dot product as the similarity function to an input vector. And so this is good because it's going to leverage the existing skills of data engineers and data scientists, which should make it easier to integrate similarity search into data pipelines. And that idiomatic SQL right there is supported by MemSQL. And so, that's going to be helpful because there are many domains and applications that are going to benefit from this kind of similarity search, right? We saw visual search in e-commerce. bioinformatics, genomics, right? We're looking into that, and there are several other domains that are starting to use this kind of similarity search right now. All right, let's talk about our chip. So there's a picture of our chip there. And if you've ever looked at chips at this level, it probably looks a lot like memory. And you would be right. In fact, we've leveraged our deep experience over the last 2 decades in high-performance memory, and that's informed the design of this computational memory chip. With some key differences. And one of the differences is depicted right there. So right next to the memory cells in this chip, depicted in the blue and yellow, we have computational circuitry that we call bit logic. And that bit logic is highly programmable. And it's interspersed evenly throughout the chip. And there are 2 million of those per chip. And often we call this in-place processing because we are manipulating the data where it lives in memory. Our consumer solution is going to be a PCIe board. Each board is going to have 2 chips. Each chip has 128 megabits of cache, and each board has 16 gigabytes of DDR4 memory. And then, we're going to do the things you would expect. You can cluster multiple boards together in a chassis, 4 boards for a 4U chassis for larger databases that are larger than 1 board, and multiple chassis solutions for databases. I think we plan to support databases up to 1 terabyte or around that range. So one of our early adopters we're working with in bioinformatics, they asked us to support network-attached storage. These guys tend to keep a lot of their molecule databases and genomics databases on file servers. And so we'll be supporting RDMA for network-attached storage. And so, because the data is numeric, we can do some tricks to segment the database using numerical techniques in offline clustering like k-means. And this is going to be tremendously useful to avoid these full database scans, much like indexing in a traditional database. And we'll be able to support faster performance in a lot of cases. Availability. So we finished the design of our first chip. It's probably being printed on silicon as we speak in Taiwan. First, silicon is in Q4 of this year, demo boards Q1, and late Q2 mass-produced boards.
What's your geometry?
Can we hold on to that in 1 second?
Jump all the way.
Sure. So, our early adopters are getting pretty excited about getting their hands on this. This is a quote from a computational chemist at the Weizmann Research Institute. And they're really excited about speeding up their molecule similarity search. And here's why. Their current approach for doing this is based off of an application that's big in biopharma, the Biovia pipeline pilot application. And right now it takes a query against a database of 34 million molecules 10 minutes. And we estimate that with our chip, we're going to be able to reduce that significantly. And we'll be able to support batch queries, which is a capability that they don't have right now. So the integration is pretty straightforward. In their application, Biovia, it supports third-party Python modules, and so integrating through our Python support is super straightforward, not too complicated. We imagine that most other applications will integrate through our C library, including in-memory database applications. one thing to expect with in-memory integration of our chip is a pretty good boost of performance compared to the state of the art, which we believe is MemSQL right now, since they publish these numbers. In their similarity search, we can boost performance by a good factor of 2. I mentioned our early adopters program. Right, there are a lot of benefits to getting in early now. I'll emphasize that we're going to produce a limited number of test and demo boards. So getting in early is good if you want to actually get your hands on hardware. And we're getting really excited about getting our first chips and first boards, and we'll be talking at some of these upcoming events. ODSC, which I believe is in this hotel, at this venue in November, PyData in DC. December, we're going to have first hands-on workshop where you get to use the software, use our simulator, learn a lot more about the chip and the technology. And we're hosting our first meetup, and I spoke to the folks here at In Memory, and it looks like they're going to use our facility for one of the next meetups in October and November. And of course, 2019, we're going to have our first chips and boards. That's really all I wanted to say. If you're interested and you want to follow these developments and where we're speaking at and where we'll be demoing, follow us on Twitter. We write a lot about visual or similarity search in the various domains that it fits into, this technology fits, on our blog. And also there's an email there if you want to get in on the early adopters program or if you have any other questions that you might have. And the workshop too. I think we're going to offer complimentary admission to anyone at this conference. All right, and so I imagine that a lot of you will have some very specific questions about the hardware, and I might not be able to answer all of those, but I have a partner in crime here, Pat Lassiere, who might also know some of the answers to those questions.
How do you spell his last name?
He's right back there. So, questions? Yes.
Apologize for coming in late. And so my question is going to be probably uninformed, but I'm curious how you handle multi-dimension similarity searches. My question is coming from the Jakarta Similarity Index, which uses for matching, say, reference data of customer addresses and names for assigning identifiers and so forth. How does that relate to the translation into associative arrays if you have, say, 25 different elements that you're trying to match between two universes of data? I'm very interested in the technology because of this problem, but I'm not sure if it's really suitable for the domain.
Yeah, so all this chip does is it will take a database of vectors, and you can think of it as a highly vectorized processor, right? The simpler the similarity function or the distance function, the better. But the data has to already be, I think, encoded as numbers that's suitable for the domain.
Would that normally be in a continuous stream of relative degree comparison, or some type of match or don't match, binary type of concept, or is it arbitrary?
Yeah, so that's a good question. And usually when we talk about that, that's the offline training process or feature engineering process that encodes the vectors. So you may have not seen the two examples, but the two examples were pretty important. The Bioinformatics one, that's where it was heavily feature engineered, where the domain scientists, right, figured out that these are important functional groups and their presence or absence is determinant in similarity. And then on the flip side, visual search, that's all trained via neural networks. And so, right, if you imagine you train a neural network with classifiers, and you remove the topmost fully connected layers, and you have a feature extractor, and those are the numbers. Those are the vectors that I'm referring to.
I can see how that would work for that case. I was curious about the structure of that in comparison to policies for Relay.
Yeah, there has to be some offline process that encodes that into a numeric representation that makes sense to that. I come from AI and ML, so I think of loss functions, and so there has to be something that can encode that space as numbers to reduce a loss as you train, which is a one case of how to get these kinds of domain relevant numbers in high dimensional computing, hyperdimensional computing, which is a new word I learned, a new term I learned today from the speaker up here.
Gil Russell.
Gil Russell, yes.
To answer your question, you need graph analytics, all right? And graph analytics is kind of the product of choice of being able to take all of these hypervectors, is what we call them, and connect them together. If you saw that visualization that I ran from Google, the reason I ran it is that's one of the best introductions to what hyperdimension is all about. In other words, if I have an aircraft and it happens to be, let's say, a Boeing 787, I can connect every part in that aircraft, all right, with the object database down to the rivets that go into the wing, their position of the aircraft. It's we're talking about a brand new database capacity based on something that is mind-boggling. I won't go into take the time of, but the idea is the graph analytic is the node is your object, and the edge vector is your distance between the next node in that particular Hamming distance or cosine distance. This is an extremely important part that GSI has done. In fact, this probably accurate, right?
Yes.
Yeah.
Yep.
Is the progenitor of this. He used to work for Neomagic, as a matter of a long time ago.
Yep, that's right.
So he's very familiar with GRAMs and high performance type of memory. He also has one that he also has a lot of patents on one that does floating point and distributed floating point, as a matter of fact, sparse distributed floating. And that's a really interesting part also, by the way.
Yeah, it is.
But this part is, this is the hyper, I'm going to get that wrong. How do I say this? This is the hyper-associative processor, basically, is what they call it, I think. It's really what it is.
Yeah, when I joined it, we started using, we threw around the term in-place associative processing.
Yeah, that's what I would have called it 3 years ago, but not anymore. Yeah, it's hard to get your, what's the handle? I don't know.
It really is.
It is. But the one point I want to say is in genomics, which is tight in this community, in this area, has a lot to do with the geography of where this is being done. This is such a hot property. I don't know, it's anybody that doesn't think this is really hot, and in genomics, and also we're having everybody knows what CRISPR is, right? Cas9.
Mm-hmm.
Well, guess what? These guys are going crazy with all sorts of solutions now to all sorts of really unbelievable problems. And also, we just made the discovery last week, was announced, was that they found that DNA actually provides the neonatal brain, or the natal brain, with the bootstrap. It actually is like a ROM code for the brain. And that's a really large discovery. Going forward, what's your patents on this? How many have you filed for?
How many patents do we have on just this processor technology?
Yeah, well over 20-something.
Yeah, it's.
We have all the patents you talked about, all enough patents. We have all the prior patents, and we have many more that we've gotten in the last 3 years since it's been over.
What's the power ratio?
The power consumption?
Yeah.
So, if I'm going to channel the project manager in Israel, he says that our power consumption will be significantly less than the GPU equivalent of
I think the
of this.
last I saw was like 8x or something like that.
Yeah.
Yeah. All right. One of the issues is that are you benching this against NVIDIA?
What do I want to say about benchmarks?
I mean, for similarity search, they're not really good at that CPU today. If you look at most similarity search, it's not cracked.
Yeah.
That's not we benchmark against. Right, that's more training, right? We don't benchmark training. So really, it's a CPU is who you benchmark against it. And I mean, the only benchmark we put is that was a CPU that you put up in the
Yeah.
Biovia.
Yeah, the tricky part about comparing with NVIDIA, I'll be honest here, is you're comparing it against parametric inferencing, and I'll say this publicly like right now, we're not going to beat parametric inference on the GPU with this version of the chip.
Yeah, that's a good motif, as I would say.
Yeah.
Stay out of their way.
Yes, exactly.
I did the hyper search engine in 2006, right, using VRAMs, and that came to a very quiet. I don't know what happened to it. You know, those people went away, and they don't have a tendency to call you up and chat.
Yeah.
So I'm very familiar with what you're doing. What's the geometry?
I'm not sure how to answer that question.
Is it 0.28?
Oh, what is the fabrication node?
Yeah.
28.
It's 28.
Okay,
Yeah.
and is that TSMC?
Yes.
Okay.
Yeah, we're slowly coming out of stealth.
Are you doing anything with Samsung?
See a few things I can't comment on.
Hey, it's my job to ask questions.
Yeah, these are great questions. Thank you.
It's almost a Weizmann right now.
Yes.
Yeah, I'm using my hetero-associative capabilities.
You are. You're doing very well in this sparse space. You're doing quite well.
Can I ask
Yes.
a basic question? Do you have any sense of the cost range for the demo board or the PCI card when it hits the market next year?
How much you got?
Yeah, that's basically our conversations, right? We're letting the market determine the cost.
It's a little early.
It is very early to talk about that. But you know, every time there are serious discussions of that, you know, GPU, right? That comes up as as something that you got to compare against. Even though the functionality is not the same, right? It's a PCI board.
Where's the best place to park at UCSF Med Center?
In the center, at the origin.
I'm talking about the genomics lab up in the hill there.
Yeah, we're super excited. You know, it's interesting, bioinformatics, right? We started out with molecule similarity, right? Totally makes sense that it's a good fit for us. And the fingerprints are small, and it's it's a straightforward similarity function. But the more we started to dive into bioinformatics, the more we're starting to see a good fit with respect to genomics. And right now, actually, NVIDIA publishes an interesting number, which is for a particular kind of genomics workload. Pat, I forget what it was, but they published that a DGX board, a DGX1, can process 13,000 genomes in a year, I think, for this particular problem.
That's all?
That's it. I think it was invariant. It was doing the
okay. Yeah,
right,
okay.
right. 'Cause so they have to process the full genome. So
because it's called a GPU on a stick. The problem is they can't get the memory. They're
Yeah.
on the PCIe.
Yeah,
so
yeah,
they're
yeah.
not in the main memory channel, so they're screwed.
yeah,
And that's their problem, by the way. Sell their stock, period. Dump it.
well, you talked about the trough of disillusionment of deep learning, and I think there's evidence to point to this nearly everywhere. I have good friends at NVIDIA. That's the new joke, right?
Yes. No, it's he knows what the issue is. All right.
Yeah.
The problem is it's like Nintendo and the new game, right? And what do you do with you've got a stream, a product stream, and you're running a business, and all of a sudden, what are you going to say? You're going to do, you know what an Osborne is?
Oh yeah, Pat actually introduced me to Osborning.
That's an Osborne, okay? That's the real issue. Yeah.
All right, very good. Yes, I'll put the contact information back up if you have
You got a card?
any questions. Yes, I do. All right, thank you very much.